We're going to go back to 1937, 71 years ago. That's when Turing wrote one of the most significant papers in computer science. He was interested in the nature, this was 10 years before the first computer was built, the first digital computer, so he's way ahead of his time. And he was interested in the nature of algorithms and in automating algorithmic thought. And in this paper, he described a hypothetical machine, which we all call the Turing machine today. And the Turing machine was never intended to be built, but it was a thought experiment. And the Turing machine consisted of two components. One was a paper tape, like this paper tape. And the paper tape was divided into squares, and each square was a symbol. You could write a symbol on that paper tape. The second part of the machine was a box. And the box could do three things. It could read a symbol off the paper tape, it could move to a new location on the paper tape, and it could write a symbol on the paper tape. And it would do so based on what it was currently reading on the paper tape and its current internal logic. Now, of course, this became the foundation of all digital computers to be built in the future, where the paper tape is directly analogous to the linear memory that we use in computers, and the box is a CPU. Turing subsequently went on to show that such a machine would be a universal machine. He said it could emulate any other machine. And it's important for my talk to know why he said that. Of course, it turned out to be prophetic and true, because computers emulate almost everything today. It has to do with the way memory is stored on a computer, which is fundamentally different how it's stored in our brains, so that's why I'm going to talk about it for a bit. The memory in a computer is purely symbolic. The symbols and where you write them are completely up to the programmer. So any particular symbol on the paper tape or in the computer's memory could represent anything. It can be your hair color, your age, the temperature outside, a snippet of music, a piece of financial data. It's unlimited. You can put as many into the memory as you have memory, only constrained by the size of the memory. You can organize them in any way. The computer does not care how you order these things. It is a purely symbolic system. And of course, you can then do any set of logical operations on those symbols. It is not constrained at all by the hardware. It is a purely symbolic system, and therefore it can emulate anything. Brains are not like that. Now, Turing was also interested in computing intelligence. In fact, he wrote another very influential paper in 1950 called Computing Machines in Intelligence, in which he said brains must be a machine. He didn't believe in magic. Brains must be some kind of machine. We can therefore emulate brains with computers. Therefore, computers can be intelligent. He didn't want to argue about what intelligence was or wasn't, or whether we could really do this, so he proposed the famous Turing test, which is essentially if a human can't tell the difference between another human and a computer by asking it questions, we'd have to say the computer was intelligent. This idea really struck people, and they got excited about it. It was a number of years before computers were even remotely powerful enough to start working on this, and that was in the year 1957 when the first AI conference was formed, and that was at the Dartmouth conference. And people started to do what Alan suggested. At first they said, let's take stories and feed them to the computer, or ask questions, or have the computer answer those questions. It turned out to be really, really hard. They couldn't make any progress on that. The next thing they said, let's try some simpler things. Let's try showing pictures to the computer and have it tell us what the picture is, or have it recognize spoken words, or navigate a robot through a crowded room. All these things turned out to be extremely difficult. In fact, the easier it was for a human to do things, the harder it was to seem to get a computer to do it. So what's the problem? This hasn't really changed in 50 years. What is the problem? Well, it was a surprising answer. In the beginning, people said, well, our computers just aren't fast enough or they're not big enough, which was undoubtedly true, but it wasn't the root cause of the problem. And everyone who worked in the AI field for any length of time ended up concluding the same thing, which was, I think, no one anticipated. The problem of making machines intelligent is one of knowledge representation. How do you put knowledge into a computer? The computer has to know an awful lot for it to be to do these things. It has to have a lot of knowledge about the world. And it wasn't all clear how to do that. I'm going to read you a quote from Patricia Churchland. Patricia Churchland was a philosopher and an AI scientist. He wrote this in 1990, at that time, as a retrospective on the difficulties of computer intelligence in AI. Here's what she had to say. She said, realistic performance of the computer required that the computer program have an extremely large knowledge base. Constructing the relevant knowledge was problem enough, and it was compounded by the problem of how to access just the contextually relevant parts. She mentions three problems here. One is it takes a huge amount of data and storage of knowledge to make machine intelligence. Second one, we don't know how to collect that data. And third, even if we did know how to collect the data, we don't know how to organize it in some useful way. Those are pretty difficult problems. I'm going to illustrate them now with just a couple of examples. We're going to start with a short story. And I'm going to read it to you. There's a short story. Mary saw the puppy in the window. She wanted it. Now, I'm going to ask you a question. What did Mary want? And you'd probably say, well, Mary wanted the puppy. And I say, how do you know that? How do you know that Mary didn't want the window? And you'd say, well, maybe puppies are more desirable than windows? Something like that? Well, if that's true, that means to understand a simple story like this, you'd have to understand the relative desirabilities of all pairings of objects, possible pairings of objects. That seemed a very difficult thing to do. I could ask you, can Mary pick up the puppy? And you'd say no, and I'd say, why? And you say, because there's a window in between, which requires that you need to know that windows are things you can see through but are physical barriers. I could ask you, what could Mary do to pick up the puppy if she really wanted to? You might say, well, she could open the window, she could break the window, or she could go in the door next to the window and ask the pet shop owner. The point of this is even a very simple story like this takes a huge amount of knowledge about the world. And if you want a computer to understand a story like this, you have to have the computer have that knowledge. And people did not know how to do that. They don't know how to collect it, they don't know how to get it in there. I'll show you another example. I have a friend who's a computer scientist who studies computer vision. And a few years ago, he came to me and he said, Jeff, let's create the grand prize in computer vision. We put up $1 million prize. I would put up $1 million prize. That was his suggestion. And then we put a challenge out there. And if it was a really difficult thing no one could do, but maybe it would motivate people to work on that. And I said, okay, what would be that challenge? He said, well, I'll show a computer pictures of cats and dogs, and the computer has to say which are the cats and which are the dogs. That's the $1 million challenge. It shows you how far away we are from solving these problems. Now, here's a bunch of pictures of cats and dogs. I assume you have no trouble seeing which are the cats and which are the dogs, at least if you're relatively close up front here. A 5-year-old could do it. Probably a 3-year-old could do it. The question we want to ask is, what kind of knowledge, what kind of information do you have to solve this problem? What kind of knowledge would a computer have to have? Well, you might at first think, well, we'll come up with some sort of template for a cat or a dog, either a representative picture or some sort of parametric description of a cat or a dog. And that doesn't work. It's impossible.